Hi gang, MATH6500. Switching gears from Brown Forsyth to another um, way to assess constant variance called the Brush-Pagan test. Actually, Brush, yeah, whatever. All right, gang, MATH6500. Switching gears from Brown Forsyth to the Brush-Pagan test to assess a constant variance assumption. Um, Actually, I'm pretty sure that there was a third name on this. I'm pretty sure it was Broish Pagan Guilford or Godfrey or something like that. But there was actually a third name, and for some reason, this person uh, got axed when we refer to the test these days. So anyway, Broish, I believe an Australian. I probably should have looked this up, shouldn't I? But anyway, just shooting from the hip here, the assumptions of the test are, not shooting from the hip. Something we should know. Large sample, errors need to be independent, normally distributed, and we switch gears a little bit here and examine the variance at each level of x, and not necessarily the variance of all the errors. So we denote that with the variance of I. And these variances at each level of x are actually related with log base e. The variance of I, gamma 0 plus gamma 1 times x sub I. So this implies that the variances at each level increase or decrease depending on the sign of the slope. So you'll find this is a much easier. Really, the Brown Forsyth isn't a difficult. It's just kind of difficult in R where we have to manipulate the data. But still, the results here are very straightforward. If we have a constant variance, then the slope of the model is equal to 0. Actually, I should say if the slope of the model is equal to 0, we assume constant variance. If the slope of the model is not equal to 1, then not equal to 0, then we do not assume constant variance. All right, so the process is pretty straightforward, kind of unique too. I think it's kind of cool. First thing we'll do is we'll regress y on x, and we'll observe the sum of squares for the error term. Next thing we'll do, once we create this model, we'll have our error squared. Then we'll regress the error squared on x, and we get what I would call a kind of a modified sum of squares regression. That's the reason I have the star there, because it's not, if it was from this model, I would just have SSR. But since it's from this rather unique model, I put the asterisk there. Next thing we do is calculate the test statistic. It's a chi-square test statistic, degrees of freedom 1. And we take the sum of squares regression from the, again, unique model divided by 2, and sum of squares error from our original model divided by n. Square that, calculate the p-value. If p-value is less than 0.05, we reject the null. If it's higher than 0.05, we fail to reject the null. Let's see how it works. The first thing we're going to do is just create a standard model. And really all I need here is just so let's just go ahead and start putting some things in. N is, what 55, I believe. So I need the sum of squares error for this model. So that's going to be super easy to find with R. So 3819. And then I need the sum of squares regression for the second model. So I'm going to do the same thing, except I'm going to do the residuals of the model squared, since I didn't save those, and again regress this on X. Get my ANOVA for this model. Probably should have named it something different, but that's cool. And so the sum of squares for the regression is 119,826. So if I could put that in my calculator without doing something goofy, it's going to be an easy problem. So 119,826 divided by 2 divided by 3,819 divided by 55. Squared. So there's what I get. All right, so I get 12.43. And so now I need to calculate the p-value. So remember, guys, in the chi-square distribution, it is a right tail distribution, so I need 12.43 there, and I need the area to the right of 12.43. Well, that's going to be super easy to get. I just need to take p chi-square, and I need 12.43. Degrees of freedom 1. Actually, that's going to give me the area below. So I need to take that away from 1. And I get a 0.0004. 2, right? So we have statistical significance at the 0.001 level. So what we would do is we would reject the null and conclude that the slope is not 0, and therefore we would conclude just like we found with the Brown-Forsyth, that we cannot assume constant variance. All right, so I think you find that this is a lot more straightforward. Really, the Brown-Forsyth, there's not much going on there. It's just a little challenging in R to divide the data set into 2 groups and do the calculations. But again, nothing there. So now in your tool bag, you have all kinds of things that we used to assess normality. Now you got a couple of tools to assess constant variance. All right, that's all I got. Take care.